All right, so it's time to go ahead and begin. So it's already the 8th week. So like I mentioned, this is the last in-person lecture of the quarter. And remember, Thursday is the open lab. Lab 6 is due Friday. And then the last 2 weeks are dedicated to the final project. Okay, both the individual during week 9 and the team final project during week 10. So I will talk in detail about those final project or the final project again. There's 2 parts to it. So, if I say plural, I'm just referring to the 2 parts of the final project. And also, I will give you your midterm scores, and I'll talk a little bit about the midterm. But before we get to all that, there's some information today. In fact, the whole lecture today is really information you need for your final project individual. Okay, because the final project individual is a 4-bit multiplier. Okay, where you're using an FSM that you designed along with 3 modules that we provide. Mealy's module, which you've already dealt with in lab 5, and it's also part of lab 6. Or no, actually, it's not part of lab 6. It's only part of lab 5. And then the ship register that we talked about last week, and every table should have code for the ship register. It's just there for reference. And also another module in that 4-bit multiplier is something called an accumulator. Okay? And we'll talk about an accumulator in just a few minutes. And the code on each table, you should have a handout that has the code for the accumulator. So, I have the handouts with the code for both the ship register and accumulator. But those modules are provided for you. They're on Canvas. So it's not like you're going to have to type that code into a file, because the files are already there. The handouts are just so you can look at the code while we talk about it. All right, so anyways, this is the agenda. And the first thing is what an accumulator is. So here's the block diagram. You have a symbol for an accumulator. It has a D input, just like a register or a counter does. It's got a Q output, okay, just like any sort of sequential circuit has. It has a load input. Again, load input's the same as enter. It has a clear. You've seen clear now on a number of different devices. And it also has a clock because it's a sequential device where it has memory. So an accumulator has a specific purpose, and its purpose is to keep track of a running total. And that's where the name accumulator comes from. Its output is just going to be, the number that continually gets updated, and it's keeping track of a running total. Now, if you take a look at a handout that has the code for the accumulator on it, there should be a blatant typo. You can tell me what the typo is in that code. It's within the always FF block. Should be something that should be screaming to you that it's a typo. What did we talk about? What's the big difference between is it? No, in this case, we do want a 0 because you'll see that the ship register, when we talk about binary multiplication, we want that, effective of multiply by 2. But remember, you only get that if you bring a 0. That's not it. It's actually syntax.
Always have to be find an arrow.
Right. Yeah, exactly. Remember. Yeah, when you assign something within an always FF, you got to have the less than here along with the equal to make the arrow sign. Remember, you only have the equal within an always column. Okay, so that was just a mistake I made when I typed that up. I should have just did a screenshot from my code, because I had it right in my code. It's just when I was typing that in Word, I forgot to see that. So anyway, that's the typo. Okay, so looking at that code, if our clear is 0 and the LD, the load, so if you look at this handout, that's got the code for the accumulator. If our clear is 0 and our LD, which is the load, is equal to 1, what's going to happen? Looking at that code. What do you see when you look at that if statement? It's an active high clear, so if clear is low, is clear going to happen? No. Clear would have to be a 1, right? In order for the output to go to 0. So if we're not clearing and we're loading, right? Because our load is an active high. So what happens?
We're adding our D to it here.
Yeah, it's just going to take whatever your Q is and add D to it, right? And if you look at the code, right? If you're not clearing, right? You see that else if you're loading, which is an active high, it's just going to assign the Q plus D. That means it's going to take whatever Q value we have, add D to it. Now that's the new Q value. Okay, and as long as you're not clearing, and as long as load is activated, it would continually do that. It would continually just update Q with D. So that's where it's keeping track of a running total, right? When you're loading. Okay, so this is just Q is going to be assigned Q plus D. Okay, but if we're not clearing and we're not loading, right? Let's say clear and load are both 0, right? So again, since clear and load are active high, if they're both 0, we're neither clearing nor loading. What's going to happen? What's the accumulator going to do? Because you've seen this in other devices. Because what's that if statement missing? By default. Well, default goes with the case statement. But what's the last thing that you should have with an if statement, unless you're trying to create something? Yeah, it doesn't have an else, right? Except the if, except the else if, but it's missing an else, and that was done on purpose because if you don't put an else with an if, what happens? Right, you create a lat, and that's the story. Right, so if this accumulator, if you're not clearing it, you're not loading it, that's when Q is just going to remain the same, right? The next data Q is just going to equal to next data Q is just going to equal present state of Q, right? That's storage. Okay, so with the accumulator, if you're not clearing and you're not loading, it's in storage. It's just going to keep whatever output it had previously. Okay, so really the accumulator works just like a register or a counter. The only unique feature is this, right? That when you're loading, it's keeping a running total at the output. Okay, so is there any questions on how an accumulator works? You're going to see how both the accumulator and the shift register work into binary multiplication. Because you're going to see when you multiply, there's a need to shift bits, right? Because like we talked about last week, if you shift to the left, you're going to get a multiply by 2. Right? Like every shift to the left gives you another multiply by 2, right? So 1 shift to the left, you get it times 2. 2 shifts to the left, you get it times 4. Now again, granted, you're bringing a 0 into the shift register, but based on our discussion last week, it should kind of make sense to you that hey, if you got a multiplier that's multiplying binary, kind of makes sense that there'd be a shift register involved, right? But shifting gives you multiplication by a whole number power 2 if you shift to the left. Well, the other thing you're going to see that you didn't see last week is that also when you're multiplying in binary, there's a need to keep track of a running total. Okay, and that's what the accumulator provides. Okay. All right, so let's go ahead now and let's talk about binary multiplication. Okay, so I think the best way to learn about binary multiplication is just to do some examples. Okay, so I've got 3 examples of it. So we're going to start with this. Okay, we're multiplying these 2 3-bit binary numbers. And you can see I'm calling this top one A, and I'm calling the bottom B. Okay. Now before I show you how to do this multiplication in binary, let's just convert these to base 10. Okay, just so when we get an answer in binary, we can check and make sure it agrees with what our base 10 number should be, right? So what is 111 in base 10? Right, that's 7 in base. What's 110? 6. So we're multiplying 7 times 6. All right, so obviously we should get an answer of 42. All right, well, this is how you multiply binary numbers in binary. The key thing is you're looking at the second number. And we're going to start with the least significant bit. And anytime you have a 0 in that second number that we're calling B, you're going to add 0 to whatever your total is. Whenever you have a 1, you're either going to add A or you're going to add a shifted version of A. And you'll see, when it's just A, when it's a shifted version, like I said, as we go through these things. So the first thing I'm doing here, see, I'm looking at the least significant bit of B. Since it's a 0, I'm just going to put zeros for what's going to be part of my total. Okay, so I'm just writing 0 since that was a 0. Okay, now I look at the next bit of B, and it's a 1. Well, when this bit of B is a 1, I'm going to add to my total a shifted version of A, and when it's this bit that's a 1, I shift A 1 place to the left. Okay, so I take A and I shift it 1 place to the left. And obviously that would be a 0. You can write a 0 there if you want. Okay. All right, then I go to the next bit of B, and when this bit of B is 1, I'm going to add a shifted version of A to the total, but this shifted version is shifted 2 places to the left. So I take A, and now I shift it 2 places to the left, and I'm adding that all to what I have. Okay, so any questions how I got this far? Do you see how I'm getting this? Okay, now we just go ahead and add like you normally. All right, so obviously 0 here, 1 here, then I have 0 plus 1 plus 1, which is 0, carry the 1, then 1 plus 1 plus 1, which is 1, carry the 1, 1 plus 1, which is 0, carry the 1. Now, if I did this correctly, this should be 42, right? So let's see, we don't have a 1, we have a 2, we don't have a 4, we have an 8, we don't have a 16, we have a 32, right? So 32, 8 to 42. And you can see we got the right answer. All right, so any questions on what I did there?
No, we did, but if you was 0 instead of that'll be a next.
Yeah, we got another one coming up. So yeah, I didn't cover all of it yet. Okay. All right, so let's do another example. Okay, here's the next example. So what are we multiplying here? What are these 2 numbers in base 10? What's 101 in base 10? 5. So we're just multiplying 5 times 5. And by the way, of course, it doesn't matter what numbers I'm multiplying. The approach is always the same, right? I just had to pick some numbers, and I just kind of did this somewhat randomly. It wasn't totally randomly because there were certain things I wanted to show. All right, but anyway, to multiply these 2, we follow the same process that we did. Okay, we're looking at B. So you're always looking at B. All right. Well, now look, this is what's different than this previous one, right? Because here the first bit, which is always the least significant bit of B that you look at, it was a 0, right? So we just put 0. But when this bit of B is a 1, you just write down A, and you don't shift it. If this is a 1, you shift A by 1 place. If this is a 1, you shift A by 2 places. But if this bit of B is a 1, you're just going to add A to the total. So you see, I just write down A. Okay. Now you get to this bit of B. Well, anytime a bit of B is 0, you're just adding 0 to the total. Right? It doesn't matter where the 0 is. Any 0 in the B number, you're just going to write down zeros. Or you could just leave it blank if you want. I'll just write down 0. It doesn't really matter where you write them, right? Okay. All right, and then we get to this bit here, which is a 1. So just like here, when this bit was a 1, we're going to add A shifted 2 places to the left. Okay, so we take 1, 0, 1, right, shift it 2 places to the left, and then this is what we have. Okay, and then again, you just add like you normally do. So 1, 0, 0, 1, all zeros, 1, 0, 1, 0, carry the 1, 1. All right, we can check if we did it right. We got a 1, we don't have a 2, we don't have a 4, we have an 8, we have a 16, so 25. So get the right answer. All right, so any questions on that? You ready for the last one? Last one's a doozy. Because what are we multiplying here? 1, 1, 1, 1. But in base 10, what are we multiplying? 15 times 15. Now, to fit in what we're going to have to add here, I'm going to need some more space. So I'm going to erase what's in blue here. There's no question. So everybody understand what we do here? Where I erase it? Just need more space. You'll see. All right. So yeah, again, we're just doing the same approach, but here, because B is all 1s, we're going to add A to a shifted version of A 1 place, to a shifted version of A 2 places, to a shifted version of A 3 places, right? Because every time you have a 1 for B, you're going to add A, right? When the 1 is here, it's just A. When the 1 is here, it's A shifted 1 place to the left. This is where I have to keep my columns straight because it's easy to get skewed. Okay, 1 here, it's going to be A again, shifted 2 places. And then A again, shifted 3 places. You see, I have to add all this. All right? Okay, so here, this is just 1 with a bunch of zeros. That's 1. Okay, here, this is 1 plus 1. That's 0. Trying to keep this all on the road here. Carry the 1. Okay, now we get to something you haven't seen before, right? Because prior to today, you saw like the addition of 3 1s, right? Which gives you 3, right? Okay, but here, look, this column here, because we carried this 1 over, we got 1 plus 1 plus 1 plus 1, which is 4. So what I can do is, remember, 4 is 1, 0, 0. Right? That's 4 in base 10. So I write this 0 in my result, and then I carry the 0 and the 1. So you see this 0 gets carried to this column, and this 1 gets carried to that column. So you see I carried this 0 and this 1 to the next 2 columns over. Okay? That's something you didn't see that before. All right, but now here we got 0 plus 4, 1, so I'm going to do the same thing, right? It's going to be 0 here, carry the 0 to this column, carry the 1 to that column. Okay, now I'm here. 0 plus 1 plus 1, which is 4 again. So it's going to be 0, carry the 0, carry the 1. Okay, then let's see. I'm on this one. Okay, 0 plus 1, that's 3. So 1, carry the 1. Then 1 plus 1, 1 plus 1 plus 1 is 3 again. So 1, carry the 1. Okay, if we did this right, we should get what? What's 15 times 15? What is it? 225, right? All right. We got a 1. We don't have a 2. We don't have a 4. We don't have an 8. We don't have a 16. We have a 32. We have a 64. We have a 128. Right? So it's 128 plus 64 plus 32 plus 1. Does that come out to 225? Let's see, 12, 14, 15, carry the 1, 3, 9, 12. So you see it did come out correctly, right? 225. Okay, so to summarize, and this is what's really important to understand in order to understand how your 4-bit multiplier works, which again is part of your final project. That's the final project individual. Is that when you're multiplying these binary numbers, B determines what you're going to do, right? The bits of B determine what you're going to do, right? Because if a bit of B is 0, you're not adding anything to the total, right? It doesn't matter where that 0 is, right? It can be any of the bits. When you have a 1, if it's the least significant bit of B that's a 1, you're adding A to the total. And if it's any other bits of B that's a 1, well, it's going to be a shifted version of A that you're going to add to the total, depending on where the 1 is, right? If the 1 is here, it's A shifted 1 place. If the 1 is here, it's A shifted 2 places, right? If the 1 is here, it's just A, right? A. If the 1 is here, you're shifting A 3 places, right? And it's always to the left that you shift because that's multiplied, right? Like we talked about last week. Okay, so did these examples make sense? Because if these examples make sense, how the circuit works should also make sense. At least that's the hope. Okay, so you ready for
What's the trick with the adding the 4 1s?
Yeah, the trick is, and it's not really a trick when you think about it, because remember, if you're adding 4 1s, obviously it's 4, and in binary, 4 is 1 0 0, right? You know, when your result is 3, or when you're adding, well, actually, let's just go to the thing here. So let's see, where are the first 4 1s? Right here is when we have the first case of 4 1, right? So 1 plus 1 plus 1 plus 1 is 4, which is 1 0 0 in binary. So I write this 0 in the result, right? So you see, I wrote this 0. We take this. Yeah, I wrote it right there, right? Then this 0 and this 1 both get carried. This 0 gets carried to the next column right next to this one, right? Because I added this column. So this 0 goes right to the next column. This 1 goes to the column next to that one. So essentially all I'm doing is I'm just carrying those 2 bits to the next 2 columns in order. Yeah, because sometimes people do this and they switch this, and of course, you know, that will give you a wrong result. I've seen that. Yeah, but that's all. Okay, so any other questions so far? All right, so here is your circuit for your final project individual. Okay, like I said, there's 2 parts to the final project. One's individual, one's team. And let me turn the camera. Oh, actually, I turned it too far. That's good. All right. Okay, so you can see you have 4 modules: chip register, accumulator, Dr. Mealy's universal seg that you've used, and then FSM. So these 3 modules are provided. Okay, these are on Canvas. You can download all 3 of these. Well, this one here, just like previously, is a text file, but you already have it for Lab 5, so you can just, you know, you can just move over that file that you already have in Lab 5. And these two, like I said, just download from Canvas. Okay. And here, this module, the FSM, that's the one you have to design. That's what you have to create. Okay. So, if you look at the shift register, it should be a little bit familiar to you, or, you can look at the code on the handout that you have, but, again, you got a Q output, you got a D input, clock input, a clear. Now, notice the clear is connected to this symbol. You've seen this symbol before. What does that symbol mean?
Ground.
Yeah, it's ground. And when you write your code, what does ground equal? Zero. Okay, so the shift register in this design is grounded, or the clear for the shift register is grounded because it's an active high clear, and for this design, you don't want the shift register to ever clear. So we're, effectively we're disabling the clearing. Okay, and then we have our select. And you remember how the select works? If you don't, you can look at that handout that has the code on it. Remember, the select is 2 bits. So we have 4 choices, right? The shift register can basically do 4 things. You remember the 4 things that the shift register can do? If select is 1, what is the shift register going to do? What's the 1 option? You look at that case statement. What's that? Yeah, that's the load, right? It's just going to take whatever's on the D input and assign it to the output. So that would be called loading the shift register. Okay. And then how about if you have option 2? What if you have a 2 on the select line? What's it going to do? Yeah, it does a shift left. So that would be a multiply, right? Multiply by 2. Now, option 3, right? 3 for the select. Do you think we'll ever use that in a multiplier? Because what's option 3 going to do? It's going to shift right. And what kind of operation happens if you shift right? Yeah, it's a divide by 2, right? And this is a multiplier. So you can bet that, we're not going to ever have that select line equal to a 3 if we're multiplying. Okay, but there could be a case when you want to use this to divide, maybe for your team project, Okay, how about option 0? Because we talked about the reason why 0 doesn't appear in the case statement, because option 0 does what? Store. Yeah, that's the hold state. That's just storage, right? Where Q is just going to remain whatever value it was previously. Okay, and notice that select input of the shift register, you follow it, it goes to an output of the FSM that you're going to create. Okay, so you see this SR select output of the FSM is controlling what the shift register is going to do. Okay, all right, so that's your shift register. Then the output of the shift register goes to the accumulator. See, the Q output of the shift register goes to the D input of the accumulator. Okay, that we just talked about earlier. And remember, we talked about that if you're loading the accumulator, that just means Q is going to equal, that Q is going to equal its previous value plus whatever the D input is, right? And if load is not a 1, right? If you're not loading, then you're just storing. Okay, now if you look at the load input of the accumulator, it goes to an output of the FSM. Right? It goes to this output ACC underscore load. So the FSM, it's not only controlling the shift register, but it's also controlling the accumulator. And we do have the clear input of the accumulator, okay, not tied to 0, because there are times that we do want to clear the accumulator. And the accumulator clear input goes to another output of the FSM. So this FSM that you're creating, it's controlling what the shift register is going to do, right? Either it's loading, storing, or shifting left. And it's also controlling what the accumulator is going to do, like when it's going to get loaded and add to the total, and also when it's going to get cleared. And look at where the inputs are going. A, that's one of the numbers we're multiplying. And B, that's the other number we're multiplying. Notice that A goes to the D input of the shift register. Notice that B goes to your FSM. So why do you suppose that is? Why would B go to the FSM, which is controlling everything else? Based on what you know about when you multiply.
Because you always look at these.
Exactly. Just like when you're multiplying manually, like we just did a moment ago, we're looking at B, right? Because the bits of B tell us what we want to do with our total, right? Whether we want to add 0 to the total or A to the total or a shifted version of A to the total, right? So you see, if you understand how to multiply binary manually, it should make sense to you that B is going to the FSM that's making the decisions, right? B, the bits of B is what determines what's going to happen to A. Okay, and also whether you're going to add to the total or not. Okay, and then, Mealy's module is just there to display, right? Mealy's module is just doing, what it did in Lab 5, right? It's just taking what's coming into its input and time multiplexing so you can show multiple digits on those, 4, 7 segment displays. Now, notice that unlike Lab 5, where you had to have, Lab 4 and 5, where you had to have a validity check, here in the multiplier, we're just setting validity to 1. We're just saying the result's going to be valid. We don't have any like invalid check for this multiplication. Okay. Also, the FSM has an enter button, right? Which again enters the same as load. So, you won't want the result of your multiplication to change until you hit enter. So just like in Lab 5, where because you had memory, right? You could be changing the switches and the display would remain its previous result until you hit the enter button. Same thing with this multiplier, right? The display should just show whatever the previous result was until you hit the button. Okay, and this does have to be a button. Okay, A and B are switches, just like previous designs, but just like what was it, Lab 5, where I wanted you to have the clear and the enter button. Same thing here with the enter. It's got to be a button. If you make it a switch, you'll lose points. Okay, so this is the diagram. Hopefully, hopefully based on what we talked about with how to multiply manually, hopefully this makes some sort of sense that, why we have these modules and why the FSM is controlling the shift register and the accumulator. Now, we're going to get more detail, okay? Because what do you always start with when you want to design an FSM? What diagram? It's on the board. What? For Lab 6, has anyone started Lab 6? Not a whole lot of people, a few people. Okay, well, you have till Friday and you have an open lab Thursday. So, I mean, you got in-class time to do it. But when we talked about an FSM, when we talked about what an FSM is, and, I showed you that System Verilog code, the format that you use when you design an FSM in System Verilog. What was the diagram that you always start with before you ever write any code? State diagram, exactly. So, I got a few questions over the weekend about Lab 6, and a few of them anyway, we're talking about code, and just from the questions I was getting, I kind of thought, well, has this person done a state diagram yet? And sure enough, I asked, well, do you have your state diagram? And they're like, oh, okay. Because again, you shouldn't even think about, you shouldn't even open up Vivado for Lab 6 until you have a state diagram. Now, you won't necessarily know if that state diagram is going to work, but you should have something before you write any sort of code. Okay? So here is the state diagram, or I should say, here is a state diagram for this 4-bit multiplier. And, I give credit where credit's due. This is not my design. This is Dr. Benson's design. My design was not as eloquent as this. Okay, Dr. Benson, this is a much eloquent design. I'll explain why as we go through it. But anyway, this is Dr. Benson's design. And like any state diagram, and this is something that when you pass in, because you'll see when we talk about the final project, there's more that you have to pass in for your final project than what you've been doing for the labs during the quarter. And you know, one of the things you'll have to pass in is a state diagram for your FSM. And when you pass in that state diagram, you want to make sure that you have a legend. Okay, if you pass in a state diagram without a legend, then the person doesn't really know what that state diagram represents. Okay, so here is the legend for this state diagram. And like any legend or any state diagram, the circle represents what? Represents a state. Okay. Inside the circle, I'm sorry if this is anyway, no matter where I put it, it's in somebody's way. So these three things that I wrote here, SR select, accumulator load, accumulator clear. Since they're inside the circle, what kind of outputs do we call these? Right, they're more outputs because when they're inside the circle that represents the state, those outputs only depend on the state you're in. Okay. Then we have this curved arrow. What does the curved arrow represents? They're in between the states, these curved arrows. So when do we go from one state to the next state? On a. There's the hint on a. What's that? One. No, not a one. Sequential circuit. What do sequential circuits have that combinational circuits don't have? A clock. So I was trying to say clock edge. Right? This is, yeah, maybe you missed that when we talked about it. The curved arrow here represents a clock transition, right? To go one state to the next, it's on a clock edge, right? FSMs, because they're sequential, right? Because they have memory, they're sensitive to a clock, right? Either the rising edge or the falling edge, right? That's why in the system Verilog code, the format, that's why you have that always FF block, right? Because that's the sequential, that's modeling the sequential part of that FSM. Okay, and then you know the always cone, that's modeling your decoders, like your output decoder and your next state decoder. Okay, now here's something. Well, actually, the next thing is, okay, this right here, this B square brackets with the number sign in front. What would that be referred to? Like what goes here in the state diagram? Like in your sequence detector, that was an X. Right, we use an X symbol, and what was X? And generally speaking, remember we had, you know, we had the 3 components of an FSM, and in black I had the more, right, and then in black and blue, like there was some couple of added things. I had the mealy. Like what's added to a mealy that a more doesn't have? Exactly. That this is an external input, right? And then underneath goes what? Mealy, well, mealy, not input, mealy output. Yeah. So inside the circle, those are the more outputs, right? Because a more output only depends on the state you're in. Outside the circle, underneath where an external input or inputs, you can have more than one. That's where the mealy output goes. Okay, because mealy outputs depend not only on the state, but also on an external input or inputs. Now, you haven't seen this before. What haven't you seen before? Have you seen this? Yeah. Previous to this state diagram, it was either a more output or a mealy output. Look here, accumulator load. It's a more output and it's a mealy output. You're going to see when we get to the state diagram that in some parts of the state diagram, accumulator load is a more. It only depends on the state. But in a different portion of the state diagram, the accumulator load is a mealy because it not only depends on the state, but it depends on a bit of B. Okay, so you see, you can have state diagrams where sometimes an output is a mealy and sometimes it's a more. Okay, and you can have multiple more outputs. You can have multiple mealy. Now we don't have multiple here, but you could have, a design where you have more than one mealy. Okay, so this state diagram is a little bit more sophisticated than what you had to do for some of the exercises, and also like your sequence detector. Like your sequence detector just has one more output, doesn't even have a mealy output. But the thing is, if you have a good understanding of the basics of state diagrams, when something gets a little bit more complicated, it's not that bad. Now, over here, enter is shown like it is because this is an asynchronous enter. Okay, all right, so that's the legend. Now, here's the state diagram for this 4-bit multiplier. And, when you do your final project and you're building this, you can use this. You can use the same exact state diagram that, again, Dr. Benson designed, or you can do something different. Mine was different, works just as well. But like I said, it's not quite as eloquent as this one is. So let's look at the states. Okay, let's start here. This is called the hold state. SR select is 0, accumulator load is 0, and accumulator clear is 0. And if you look at the coding again for the shift register and the accumulator, you would see that all your inputs for those two devices are active high. So if clear is low, that means we're not clearing the accumulator. And if load is low, we're not loading the accumulator. And then, there's one exception to what I just said, and that's with the SR select, because the SR select, like we talked about before, has 4 options since it's 2 bits. But when SR select is a 0, like we said earlier, it's doing what? What is the shift register doing if the select bits are 0? Yeah, it's just storing, it's holding. So it makes sense that in the hold state, the SR select would be 0. So in this state, basically the multiplier is just kind of sitting there. Right? That's why we call it the hold. And it's not until you get an asynchronous enter, and the enter is active high, or we're going to make it active high in your FSM. Well, when the enter becomes active high, that's going to put us in the start state. And in this, now, again, you know what these double dashes mean? It just means the same thing I wrote over here. I just didn't want to have to rewrite it. So in the start state, your SR select is going to go to 1. Okay, so what does the shift register do when the select bits are 1? Load, that's the load, right? Because remember, 0 is the hold, 1 is the load, 2 is the shift left, 3 is the shift right. Now, we're never going to have a 3 here, but we could have the other, 0, 1, or 2. So when the SR select is a 1, the shift register gets loaded. And what does load mean? Look at the code. Say that again? Right, that Q is going to become whatever's on the D input, which here is connected to A. Right, so you see when you load, Q of the shift register is going to be assigned to A, right? Because we're connecting that A binary number that we want, that's part of the multiplication, to input D of the shift register. Okay, accumulator load is 0, so the accumulator doesn't get loaded. And the accumulator clear is a 1, so the accumulator is going to get cleared. And cleared means what? Cleared is the same as reset. What does reset mean? Yeah, that the output just gets assigned 0. So you see when it's in the start state, the shift register is going to get loaded. The accumulator is going to get cleared, right? You don't want to clear and load at the same time, of course. Sorry, that's why we disable load and we enable clear. Now, the key thing, and this is what can be confusing to some people. And after we step through this state diagram, I'm going to show you a timing diagram for this. And what can be a little difficult at first for some people is, the thing you got to remember is that these inputs we have here, the the clear, the load, and the select the shift register, those are synchronous. Like if you look at the code, right, they all depend on the positive edge of the clock. So even though these values get set here in this state, the loading of the shift register and the clearing of the accumulator, they don't happen until the next clock edge after these values have been set. So you see the clear and the load, they actually happen on this transition. Okay, and you'll see what that looks like in the timing diagram coming up. Okay, but just keep in mind here that, we're talking about synchronous. The only thing that's asynchronous that doesn't depend on a clock edge is this enter that gets you into the start state. But everything after that is synchronous. Okay. All right. So this is what happens in the start state. Okay. A is going to get loaded into the shift register, and the accumulator is going to get cleared. Right. Its output's going to go to 0. Okay. So then on the next clock edge after this state, then we go into this state bit 0. And it's called bit 0 because here we're looking at this bit of B. Right, because this bit of B is going to determine what we're going to do with A, right? Whether we're going to shift it, whether we're going to have it as part of our total or not. Okay, so look what happens in bit 0. And in fact, if you look at all the bit states, right, bit 0, bit 1, bit 2, bit 3, you can see that we're setting these 3 values to the same, right? In each one of these bit states, SR select gets set to a 2. Accumulator load. Oh, actually, I made a mistake here. Accumulator load shouldn't be here. Let's get rid of it. Do you see why accumulator load shouldn't be here? Because where's accumulator load? See, it's now a mealy. It's only a more during the start state and the hold state. Once we get to the bit states, our accumulator load becomes a mealy output. Okay, so if you had this written down, make sure you erase what was there, because that doesn't make sense. That would be having the same thing as both a more and a mealy, and that, during the same state, which doesn't make sense. So that was a mistake on my part. Okay, but in these different bit states, our SR select is a 2. So when SR selects a 2, what's going to happen? What's the shift register going to do? Shift left. Right. So it's in shift left mode. The accumulator load becomes a mealy output. And then our accumulator clear, we want to be 0 because during none of the bit states do we want to clear the accumulator, right? Because once we're in the bit states, we want the accumulator to be keeping track of this total, right? So we don't want to clear it, okay? But here's the key point. And this is why once you get to the bit states, once you start looking at this binary number B, you want your accumulator load output to be a mealy because now it's going to depend on what the value of that bit is, right? Because if a bit of my B input is a 0, I don't want to load the accumulator. But if my bit of B is a 1, I either want to add A to the total or a shifted version of A to the total. So you see what Dr. Benson does in this design, and it's the reason why it's eloquent, is that in each state, she's shifting B. But she'll only use that shifted version of B if the bit is a 1. See, if the bit, I pointed at the wrong one here. See, if the bit is a 1, we'll load the accumulator, which means we're going to use that as part of the running total. But if the bit is a 0, we're not going to load the accumulator. So even though A is getting shifted in each bit state, it's only used, that shifted version is only used if the corresponding bit of B is a 1. If the corresponding bit is a 0, we're not loading the shift register, and that's the same as adding 0. Okay, does that make sense? See, that's why this is eloquent. Because when I did this design, my state diagram didn't look like this. It had more states because, I was doing it more brute force. That if the bit was 0, I was actually adding 0, right? I was loading 0. But you see what she did is she just kept shifting, but by not loading, if the bit is a 0, that's the same as adding 0, right? It's very clever. It's kind of simple, but clever. Okay, so like I said, I'm going to show you the timing diagram for this, and hopefully that will show this, or at least the synchronous portion of it more clearly. Like I said, you can use the same exact state diagram if you want, or if you want to do something different, if you want to do it more brute force like the way I did it, that's okay. Okay, did you have a question? I thought I saw your hand go up.
To clarify, but you basically just said it.
Okay, yeah, and I'm going to show it. I'm going to show a timing diagram for this. And that's actually the activity today, is just to complete the timing diagram that I'm going to show you. Okay, that goes along with the state diagram and this circuit here. Okay, but the main thing I wanted to stress is that the accumulator load for these two states, it's a more because it only depends on the state. But once you get to the bit states, it becomes a mealy because now it depends on more than just the state. It depends on what this bit is. Right? And if the bit is a 1, we're going to load the accumulator, right? With that shifted version. If the bit is a 0, even though we keep shifting A, we're just not going to load it, which is, again, the same as adding 0 to the total. Okay? All right, so let's see, it's top of the hour. Why don't we take about a 5-minute break, and when you come back, I will show you this timing diagram, and then I'll have you do the activity. Now, today's going to be a little bit different where, normally I would go through everything I was going to talk about before you did the activity. And that way, once you're done with the activity, we get to the lab portion. If you didn't want to stay, you could go. But I'm doing a little bit different today where I'm going to have you finish the activity first, and then you should stay here because after the activity is finished, that's when I'm going to go over the final project information, and that's when I'll give you your midterm score. And then after that, if you don't want to stick around, you could leave at that point. Okay, but today you don't want to leave after the activity because I got more to talk about after the activity. Okay, but let's take just a 5-minute break to, like around 8 past or so, 9 past, and then I'll pick up with the timing diagram.
Yeah, I got it.
So did you get my email about the groups that are final project?
Yeah, so I'm gonna have
Did you get my email? I did. Okay, yeah. So, yeah, the final project team that you need to together. Yeah, like I said, everything else like lab 6 and the other part of the final project is individual. So, yeah. Okay.
So I would figure that they create that thing. I think you at least something like I would
Is that pretty clear? Yeah, is that pretty clear? Yeah, I guess it's funny because with the screen, it actually, I think, hurts the resolution. I think it's better resolution. It's just on the whiteboard. Right. Well, although somebody told me, I don't know if it's a section or a different section that they installed like they installed version 22.2 like a week ago. And I guess there's been an update since like the beginning of the course. It seems like that simulation of the it seems like if you have 22.1, then it should be 22.2. It depends on when you install it. Like if you're inspecting a coding recorder, probably I mean the unit
So
I haven't heard any, no one else has had, not that I know of, no one else has had 22.2.1, but the only trouble with it is just when you try to use the simulation. Everything else is old versions. I haven't heard any other time. It was just, remember the activity where you had to drag over like the intermediate signal. Yeah, that's when the problem as far as I know,
I don't really there. It's like that for hours now. People like it in person, but it was not it was a key of not about the video there and everything. And after this and ran this file.
So there's a 2023. I don't even oh, I didn't know that. No, the person I was talking to before, at least they told me it sounded like it was still another 2022 that they I don't know if it's or something. I don't know, but maybe but that's the first I've ever heard of that. I don't know. It's the first I've heard. I mean, I've had to see what it was.
I already opened it.
It's a time to start. Okay. So let's go ahead and take a look at the timing diagram for this. So, when you go to see if your 4-bit multiplier is working the way it is, and you simulate in Vivado, well, just like your previous designs throughout the quarter, you're going to have to look at the timing diagram. So I just wanted to go over part of this, like I've done about half of it, and then the activity is for you to see if you can finish it. So first of all, like we said, the async is an asynchronous, everything else is synchronous, okay? Only enter is asynchronous. And then for what you see here, it's for when A is 7 and B is 6. So it would be the same as that first example that we went over by hand. And then if you look at the top here, and by the way, this handout that I used to, manually come up with this timing diagram, this is the same form that you'll be using in CPE133 when you take that class, because you'll see in that class, there's going to be a need for you to come up with, timing diagrams for like the different instructions for the microprocessor in that class. So this is giving you a little bit of a preview of just, looking at a form like this. So up at the top, this is where I wrote into the states. So you see right here, the hold state, start. I made the start 2 clock cycles. It's asynchronous and, it's a button, right? Because it's essentially your enter, right? That's a button. So, depending how long you press the button is going to determine how many clock cycles. Now, it's probably going to be a lot more clock cycles than what I have here, right? Because these are happening in nanoseconds and probably just pressing the buttons at least, a few thousand, if not tens of thousands of nanoseconds. But again, I just made it a couple of clock cycles. And then after the start, here's bit 0 state, bit 1 state, bit 2 state, bit 3 state, and then hold state. So it's basically showing, one path through this timing diagram. So if you look at the timing diagram here, and here's the clock, okay, just a periodic square wave. We got our enter, we got our SR select, we got our accumulator load, accumulator clear, and then here I wrote SR contents and ACC contents. What I mean by contents is that's what's going to be at the output. So, SR contents, that's what's at the Q output of the shift register. ACC contents, that's what's at the output, the Q output of the accumulator. Okay. So here in the hold state, you can see, I just looked at my state diagram, and in the hold state, before you hit enter, so enter is low, but right here, SR select is 0, accumulator load is 0, accumulator clear is 0. And then for the contents of the shift register and for the accumulator, I wrote all zeros, and I made a note here. That would be true as long as in your code you initialize those outputs to 0. You know how we talked about in the code when I showed you the format of the system Verilog code for an FSM, right before you go into, I think it's right before the always comb block, you can initialize your outputs to 0. I mean, if you didn't initialize your outputs to 0, then you wouldn't necessarily know what was going to be here. It would be whatever the simulator decides. It could be something random. Okay, but instead of putting question marks there, I wrote zeros because, in my code, I did initialize these outputs to 0. Okay. All right. So you would just stay in that hold state until you get an enter, right? The asynchronous enter, and that would put you into the start. So you see here when enter goes to a 1, because the enter is asynchronous, it doesn't depend on a clock. So you would immediately go into that start state. But the thing to remember is that these inputs that we have here, they are synchronous, right? So I mean, these do depend on the clock. Getting to the start state doesn't depend on the clock, but once you're in the start state, those inputs we have are synchronous. So in the start state, you can see that SR select becomes 1, which, like we said, is a load, right? And then accumulator load is a 0, meaning we're not going to load the accumulator. Accumulator clears a 1, which means we're going to clear the accumulator. Now, because I kept start or I kept enter a 1 for 2 clock cycles, it would just carry over to the second clock cycle, the same 1, 0, 1. Well, actually, before we get to that, and this is where the synchronous part comes in. So if we look at this first clock cycle that enter is a 1 and SR select becomes a 1, accumulator load becomes a 0, and accumulator clear becomes a 1. see, here's the synchronous part of this. Is that even though, let's see, let's look at SR select. Okay, so SR select became a 1 once we go into that start state, which means we're gonna load the shift register, right? Which means the Q output, the SR contents, is gonna equal the D input, which is connected to A. Okay, and we're multiplying 7 times 6, so A is equal to 7. So see, this is the synchronous part of what I'm talking about, because even though SR select went to a 1 at this time, the contents, the output of the shift register doesn't change from a 0 to a 7. It doesn't go from that initial value of 0 to the new value of 7 until this clock edge comes along. See, so right here, even though SR select is a 1, see that SR contents is still 0 until this 0 to 1 transition of the clock. Then it goes from 0 to 7. See, so that's when the load happens. It doesn't happen once SR select becomes 1. It happens once SR select is 1 and you have a 0 to 1 transition of the clock. Okay, so this is the key point there. See, the SR contents didn't become a 7 here. It becomes a 7 here because you need that clock edge because it's synchronous. Okay. A lot of times when I taught this, what's challenging sometimes to some people is they feel like the outputs are all skewed. Like they're like, wait a minute, everything seems like it's delayed. Yeah, because it's synchronous. That's why you're seeing sort of like a delay. Okay. And the same thing with the clear, right? When we go to clear the accumulator, we make it a 1 here. The clear doesn't actually happen until this time. Now, if you initialize the output of the accumulator to 0, you're not going to actually see anything change, right? Because clearing is making the output 0, and if it starts out at 0, it just stays the same. But if clear was initialized to something else, some other value, you would see it change to 0 at the time of that following 0 to 1 transition of the clock.
What is the first clock edge not counted when you're going sector 4?
What state are we in? The start here?
Yeah, no, the first clock edge.
Well, this one here, remember, enter is asynchronous, right? Remember, asynchronous doesn't depend on the clock.
Yeah.
So you see, once enter goes high, that will put us in the start state right away. Like to get to the start state, once enter becomes active, doesn't take a clock edge because it's asynchronous. We do that in the code, okay? But once you're in that state, these are synchronous. So it's going to take more than just having an active value for any of those inputs. It's also going to take that 0 to 1 clock edge.
Okay.
Yeah. Okay.
Yeah.
So that's the start state. Then we go into the first bit state. Okay, bit 0. So in bit 0, the SR select is going to be a 2. That's going to put us in shift left mode. Accumulator load. Let's see. Accumulator load is going to be a 0 because since we're multiplying 7 times 6 and B is 6, the first bit of the least significant bit of that B value is a 0, right? And if it's a 0, we're not loading the accumulator. Right? So that's why accumulator load is a 0, because the first bit, the least significant bit of B is a 0. Okay, and we're not clearing, right? We don't want to clear once we're in the bit state. So you can see here that again, because our shift register is synchronous, right? That select is synchronous, that the shifting of the bits of our shift register doesn't happen until this clock edge, right? It went into shift left mode here, but the shift doesn't happen until here because see, at this clock edge, that's when we went from a 7, right? 0, 7, which is what we loaded. And we go from a 0, 7 to a 0, 8. Right? Because if you do a shift left one place, you start out with 0, 7. In binary, that would be 0, 1, 1, 1. We only have 4 bits here. And then if we do one shift to the left and bring in a 0, we're going to have 1, 1, 1, 0, and that's an E. right? So by doing one shift to the left, bringing in a 0, I go from a 7 to an E. Okay, but because I'm not loading, my accumulator just stays a 0. See, it was a 0 before that clock edge and a 0 after that clock edge. Okay, and then the last thing I show here, and I want you to fill out the rest, is that in state bit 1, right, when we're in that state, and this is the same for all the bit states like we talked about earlier, we're still going to be shifting left. We're not clearing the accumulator, but what could be different is the bit value depending on what we're multiplying by. And again, since this is a 6, now the next bit is going to be a 1, which means we do want to load the accumulator. All right, and I forgot to point this out earlier, but the accumulator input is connected to the output of the shift register, right? So whatever's at the output of the shift register, that's what we have at the input of our accumulator. So when we load the accumulator, it's taking the output of the shift register and putting it at the output of the accumulator. And you see that doesn't happen until the following clock edge, right? So see here, we're loading, right? The accumulator load goes to a 1, but then the accumulator doesn't actually load until this clock edge. And that's why you see E here, right? Because that's what we have at the output of the shift register. And now at the time of that clock edge that follows when the accumulator is a 1, that's when we have the E at the output of the accumulator. Okay, so again, you're seeing the synchronous part of these inputs. All right, so did that make sense? Because that's the key thing. I mean, the whole reason I made this up and the whole reason why I'm having you complete it is hopefully that you understand the significance of when you have a synchronous input, like what effect it has on your timing diagram, right? Because it's not enough just for that input to become active. If it's synchronous, the input has to be active and you have to have that 0 to 1 transition of the clock. Okay, and if that made sense to you, then you should be able to complete this. You just got to complete it up to the hold state here. So we're just doing like one path through this state diagram. Okay, and I put the answer up here. Okay, so you can work through that and then check against mine. And like always, if you have questions, please ask. So like I said earlier, what's different this week is that, I want you to complete the activity, okay? And then once you're done with the activity, that's when I'm going to go over the final project information. That's when I'll give you your midterm scores. And then you can work on lab 6 or, stay here and work on it or go somewhere else and work on it or work on it at a different time. Okay. But the next thing to do is to work on the activity. Okay.